Hi, students. These are going to be your notes for 8.1, which are going to cover polar coordinates. So we're going to learn about a whole different system instead of rectangular coordinates, which you came in knowing about. This will become really important if you're going into engineering or physics. And so let's get started. What we know is that we can represent a coordinate as x comma y, right? And that x coordinate is representing that horizontal movement, and that y coordinate is representing that vertical movement. And we also know in this class, we can find our r, which is the hypotenuse of our triangle or the radius of our circle. So all things we've been talking about. Now, what we know before we get into polar coordinates is that if we're given an ordered pair, so like this one, root 3, 1, that would tell us to go out root 3 to the right and then go up 1 unit. And that gives us this coordinate root 3, comma 1. Well, if we think of this point as a point on a circle, so let's see if I can do my circle justice. Not too bad. All right. Then we can also think about that this is our R for our circle. Then we know the distance from the origin to this point is called the radius, which I just showed you. In addition, we can figure out the angle formed on the positive x-axis as theta. So nothing terribly new. The new thing is that polar coordinates, it uses an R and a theta to represent its location versus a horizontal and vertical movement. We will see why this can be beneficial for calculus as we go on in the notes, but right now I'm just giving you the definition. So I can figure out R because I know that this length from here to here is root 3. And I know this length is 1. So to find R, what we've been doing this entire term, we're going to use Patharian Theorem. So R squared equals root 3 squared plus 1 squared. All right, so we're going to get R squared equals 3 plus 1, which gives us 4. And we're going to go ahead and take the square root, and so we get 2. Now something different is going to happen in these notes, but for right now, I'm just going to address that my R is 2. Because pretty soon, now our R can take on a negative value. Now, what we can figure out though too is what our theta is here. Well, this is going back to when we first met, and you could use the inverse because you're looking for an angle. So you could use the inverse sine, the inverse cosine, or the inverse tangent. Personally, for me, I'm always going to use the inverse tangent. The reason being is because your x and y's were given to you, and I had to find R. So in case my R is wrong, then my inverse for cosine or cosine or sine would be incorrect as well. So I'm going to stick to what is given to me always. So I do inverse tangent, opposite over adjacent. Sometimes this is not on your unit circle, but this one is. So remember, I always want to rationalize things. So that becomes root 3 over 3. And hopefully at this moment, I'm really hoping you feel really confident about that unit circle. We're in the first quadrant, so think about location, okay? And so what this is going to give me is that, oh, my theta is going to have to be pi over 6. So what we just found is that in rectangular world, this coordinate is root 3, 1. And in polar world, let's just go back up to the definition. See how it says that my R is always first? So in polar world, it's going to be 2 pi over 6. Now, one thing that's nice about polar world is when I graphed root 3 over, or sorry, root 3, 1, I had to approximate where root 3 is. That is hard, right? It's an irrational number. It goes on forever and ever. So there's an estimation happening there. However, if I plot 2 pi 6, I can find its exact location much easier. And we'll see an example of that in our next example. All right, so going on, it says, based on our definition on page 1, where we say using polar coordinates, we can express, this is known as rectangular, which is in terms of x and y. And we know this is polar because it's in terms of r and theta. All right, so your input and your output are different. We can say that the rectangular coordinates root 3, 1 are, which we just found, 2 pi over 6. And if this is true, it should represent the same point on both the rectangular coordinate system and the circle-based polar coordinate system. So this is kind of cool looking. This is the polar graph paper we will be using. I will provide it on a worksheet if we ever need it, or you can just Google polar graph paper and see some. Now, there's a bunch of different ones, you know, it's just in how they want to divide up the circle. This one that I've chosen, it's lacking the pi over 4 line. So I would just go ahead and add it in. You can find one that would have all of them. And what it's showing here is that this right here, this circle, has a radius of 1. The next circle has a radius of 2, and so forth, okay? So I'm going to get rid of that because it's going to be a little bit busy for my liking. So I need to, and this is the key thing, when you're going to plot this, always, always, always plot your angle first. I'm even going to write that down. Plot angle first. So I'm going to go to pi over 6, always in standard position. If I go to pi over 6, that is this line right here. And then, so I'm at my angle. This right here is pi over 6. And then I count out 2. So this is a circle with radius 2, or sorry, 1. This is a circle of radius 2. And see how exact that is? That does look pretty darn close. I'm going to scoot up to where root 3, 1 was located. So I can represent this as 2, as your r is 2 and your theta is pi over 6. That's it in polar form. In rectangular form, it's root 3, 1. So they're interchangeable. It's just 2 different forms. And as we go on in the notes, it will get better of why we're even talking about polar coordinates and polar equations. And that is where I'll stop, and we'll pick up on the next video.